All right, welcome. I want to talk today about molarity and acids and bases, two things we talked about in class this week. So to start with, we're just going to kind of talk about what are properties of acids and bases, what are characteristics of them. Acids are things like you can see this picture, are fruits, the lemon, the lime, the apple, the tomato, your Coca-Cola or vinegar, of course. And then the bases are usually the cleaning products that you'll find in your house. So we're going to look at different chemistry properties of these. Other than the idea of just the basic food ones you see here, let's kind of look at chemistry properties. And that's what we did for the lab. We found that when we did the lab, well, let me go to this here. We found that acids would turn everything red. I love the way I wrote in blue, red, but whether it was blue litmus paper or red litmus paper, it kept it red. The bases would keep things blue. That's a characteristic of bases. We did see that all things will actually conduct, whether you were an acid or a base. And the reason for that is because there are charged particles and they are free to move. That goes back to when we learned what conducting means. Now, I didn't go too much further into that about charged particles free to move. We're going to draw pictures next week about what this really looks like, but what we can know from this lab is that acids and bases have to have charged particles that are free to move because it conducts. That's the only way things can conduct, so it must be present. And then lastly, when we're doing cabbage powder, if you put cabbage powder into an acid, it's going to be turning red with red for the acids. But the bases can change depending on how strong the bases are. So bases could be like a green, or a blue, or like a purple. So still on that blue end. It's just cabbage powder can have lots of different colors. Something that's neutral would have a green or a yellow, but usually the red would be our acids. And the different color of the cabbage powder was because of their different molarity. And so here's where we stop to talk about what molarity is. Molarity is defined as the moles of solute per liter of solution. So let's take a look at what those words mean first. The solute is the thing dissolved. So like if you take salt and you put it in water, it would be the salt. The solute is the powder or the stuff you dissolve in there. It doesn't have to be a powder or a solid, but more often than not it is. And solution will be all of the stuff. So it would be the water and the salt. The last thing that is not in the definition, the solvent would be the thing like the water. So the thing that gets dissolved is the solute. The thing that does the dissolving is the solvent. And then when you put the two together, you get the solution. So when we look at the definition of molarity, we're always going to think about moles of solute on top per liter of solution. It's a division sort of thing per liter of solution. So let's use that down here. A solution has a volume of 250 milliliters and contains 0.7 moles of NaCl. What's the molarity of the solution? This is kind of a plug and chug kind of one, I would call it, because I want to use the mole of solute. Solute is the stuff dissolved, NaCl, and it's 0.7, so 0.70. Taking a look at liters of solution. Now I have milliliters, so I need to move that into liters. Milliliters is a small amount. There are 1,000 milliliters in a liter, so I'm going to move my decimal place 1, 2, 3 to get myself to 0.25 liters. 0.25 liters. So if you got to go from milliliters to liters, you're going to want to whoop it, whoop, whoop, to the left. Now I'm just going to take 0.7 divided by 0.25, and I got 2.8 in my calculator. And to finalize my answer, I would say 2.8 with a big M. That's what molarity is for units. Like grams is a little g, molarity is a big M. And you would say, if you were reading this, it's a 2.8 molar solution of NaCl. 2.8 molar solution of NaCl. All right. Now, this actually lives in our mole map. If you look here, we've got moles per liter here. And if I've got a solution, which I do, I can use molarity, which is defined as moles per liter. So I'm going to use that in the mole map if I want to go from liters to moles or back again moles to liters. All right, so let's give it a go. How many grams of calcium nitrate is in 100 milliliters of 1.52 CaNO32? All right, I'm going to start it out just like any other. I want to find grams, and that's the spot on the mole map. So we'll go question mark grams equals. I want to find how many grams. So question mark grams equals. Now I've got two numbers. A milliliters, which really isn't that useful because milliliters isn't on the mole map. So I'm going to move that into liters. 1, 2, 3. So I can see that's 0.1000 liters. I kept those zeros there because they're sig figs. And then I've got 1.52 molar. So my question is, what number do I put on the other side of the equal sign? If I check out my map, you can only put stuff on the other side of the equal sign if they are a box, like a liters, a moles, a grams, compounds, which is the top part. But you can't put molarity in there because you'd be living in this like middle region here. Molarity can only be a conversion factor. It can't be like a living box, a starting and a finishing spot. So I'm going to put on the other side there my 0.1 liters. That way, when I look at where I am, I'm starting here, and I'm going to end at grams. I'm going to end right here. So I'm going to go up and then over to get myself to grams. So here we go. First part, I'm in liters. I want to get out of liters, so I'll put it on the bottom. That way they'll cancel. I'm going to check out my mole map. Okay, I'm in liters. I'm going to move myself up to moles. I'm first going to moles, so moles will be on top. I put my units in first, and then I look at, okay, what numbers do I put in? When I do this jump from top to bottom, from bottom to top, I'm going to need molarity. So I'm going to go look at my molarity. It says it's 1.52 molar. Let me take a moment to write that down. 1.52 molar. What that really means is moles per liter, per 1 liter. I know that. I'll go back to the definition. The definition tells me that means moles per liter, per 1 liter. So here, that tells me 1.52 goes with moles per 1 liter. Got it. Going on to my next step. I want to get out of moles, so I'll put it on the bottom. That way it'll cancel. I want to get into grams next. My second step is to go from moles to grams. So put grams on top. Here, when I'm going to go moles to grams, I can see my conversion factor there is the periodic table number. 1 goes with mole, so I'm going to put 1 with mole. And the grams is my periodic table number. That means I'm going to look up on there calcium. He's worth 40.078. I'm going to look up nitrogen. There happens to be 2 of them. Each nitrogen is 14.01, so I'll times by 2. I'm going to look up my 6 oxygens. 6 oxygens. Each oxygen is 15.999. So I'll add all those up using my calculator, and I got 164.092 for the molar mass, or the number of grams there is per mole. So at this point, I'm going to take my calculator and take 164.092, multiply by 1.52, and by 0.1, divided by 1 on the bottom, which I don't really need to do my calculator. So I got a 24.9. That's how many grams of calcium nitrate happens to be in 100 milliliters of 1.52 molar solution. That one's done. So let's use that same kind of concept here when we solve this problem. It says how many compounds? Question mark compounds. Compounds is a box on the mole map, so I can put that there, is equal to, now I can use one of these two. A liters thing, I'm going to make that into liters. Milliliters are really never useful. You always want to go into liters to get yourself in the mole map. 1, 2, 3. So that's equal to 0.025 liters. And 2.12 molar. Okay, I know that there's no box for molarity on the mole map, so I've got to use my liters number here. That's what's going to go on the other side. I'm going to go up to my mole map up here, check out where I am and where I need to go. I'll start writing on the other side here. Oops. So on this side, when I look over here, I am currently in liters, and I want to get myself 1, 2, up to here, compounds. So that's going to take me 2 steps. All right, so let's get out of liters and go into moles. If I put liters on the bottom, the liters will cancel. And I want to go to moles because that's my first step. And to go from liters to moles, I'm going to use molarity. Now my molarity right here, 2.12, that's how many moles there are per 1 liter. So 2.12 goes with the word mole, 2.12 per 1 liter, 1 goes on the bottom. Now I've got moles on top, I got to put moles on the bottom to get rid of them. That way moles cancel. And I want to go to compounds. I'll check my map up here. Compounds is at the top, moles to compounds. To do that, I'm going to have to use this conversion factor. 1 goes with mole, and the other spot needs the big number. 1 goes with mole. I'm putting compounds here. And the big number goes there. So now I just got to push buttons in my calculator. Make sure to use that EE button. I got 3.2 10 to the 22. All right. So then we ended the day by filling in the rest of this data table by calculating molarity. So I'm going to calculate one for you. In other words, we calculate each of these boxes. I'll do this box right down here. So what we're trying to find is what was the molarity of the solution that we made when we mixed this citric acid in there. So when we think about it, when we asked what is molarity, there's no box on molarity, so I can't do question mark molarity equals because it won't work that way. So I have to break it down. I have to look at, well, this is moles per liter. I know that when I made the solution, I used 50 milliliters of water, and I put in 3 grams of the substance. So 50 milliliters of water, 50 milliliters, I can move it over 1, 2, 3. 0.050 liters is what I used. And the moles, I don't know the moles part, but I could calculate it. Because I'm going to say to myself, well, how many moles is it when I use 3 grams? 3.0 grams, technically, to keep my sig figs. And I'm going to be doing it for citric acid here. But you could use it for any of the substances that we've got. I'm going to get out of grams and into moles. I can do that in one step using my mole map. So if I look in the mole map, doing grams to moles, grams to moles is right here in that far right. I'm going to use the periodic table number, where 1 goes with mole, and that grams is the periodic table number. So 1 goes with mole, and my grams number is going to be all the citric acid stuff. So here it's a total of 8 H's, 6 C's, and 7 O's. All right, just to warn you, in the interest of time, I got 3 minutes left of my video, so I'm going to kind of speed up a little bit. But like I said, I'm going to add my H's, my C's, and my O's here, and I get 192.1222 for my molar mass. This is my citric acid one. So then I'm going to take 3 divided by that number, and I get 0.0156. That's how many moles I've got. That moles number will go right up here. So that molarity is equal to moles, 0.0156, and how many liters? 0.05 liters. If I divide those two, I get it to equal 0.312, or 31 to keep 2 sig figs. That's all I can do for this. So that's what I'm put here, 0.31 molar. To give you the rest of the data table, so maybe you could try some. This is 0.57. And the last one on the far right is 0.71. Okay. So if you're going to be doing those calculations, I think you should give one a go. It's actually going to be the same stuff as this blue stuff. It's just this 192 number will be different. It won't be for citric acid. It'll be for Na2CO3, or it'll be for NaHCO3. So there you are. Down here, what we're looking at is what's most concentrated. Concentrated is that word that means the most amount of stuff. If I say, oh, that's a high concentration of, I don't know, whatever, you're thinking like, that's a lot of stuff in there, that you got a lot of it. So if I look at my numbers here, I'm going to be trying to separate my acids from my bases. So I will start with my bases. Here's a base number, and here's a base number. Of these 3 bases, the 3 ones I circled in blue, which one is the most concentrated? It's the one with the highest number. It has the most amount of stuff in it. I call this B1 because it's the strongest base, the most concentrated base. It has 0.71 moles per liter. While over on this side, I'll call this B2. It has 0.57 moles per 1 liter. And this being B1, it has 0.31 moles. Oh, that's an acid. Never mind. Take that back. I'm going to stop right there. This one's an acid, acid, acid. Okay, let's look at our 3 acids then. Of the 3 acids, which one's the most concentrated? I'm going to look for the biggest number, 0.31. This is acid 1. Biggest number next, A2. And the third, A3. This one is the least concentrated because it only has 0.01 moles per 1 liter. So that's just how I ranked them. To see most concentrated would be the highest molarity. That's what that would mean. I hope that helped.